Okay, so we've started, you've already talked about 11, you've gone through the lab, you should understand a little bit about the period of a pendulum, so this shouldn't be too amazing information. We're going to get through it real quick and get you on to the homework. So, simple harmonic movement, SHM. Hopefully you've already used that. The amplitude of the vibration, basically you have a pendulum's amplitude can be measured in the angle. So the amplitude is the angle going to the right and to the left. That's the easiest way to measure it. Again, always under than 15 degrees. For a mass spring, it's basically how much the distance x, how much it was compressed or how much that spring was stretched. It works in almost all of them. Now the hard part for people to start remembering is SI units of amplitude are in radians. I know I've been saying up until this point degree, degree, degree. Unfortunately, these are in radians. So that's going to be a change. You're going to have to just remember it. Simple harmonic movements you should deal with in radians. In that case, here you go. So the period, again, we're dealing with t as a period. So you have t equals 2 pi square root of the length over acceleration due to gravity. Again, almost always acceleration due to gravity is going to be 9.81. Length is going to be length of your pendulum. So that gives you your period. You should have that in notes. We're going to deal with it. Hopefully, you've already dealt with it in the lab. We're going to deal with it a little bit more during the next class period. That being said, the other part is for the period. You have another way to calculate it. You have 2 pi divided by mass divided by the spring constant, and this is only for when you have a spring being stretched. A little different equation, gets you the same period of a spring system. Again, it's still simple harmonic motion. Should have those in your notes. Now, this is where it's going to be a lot of review, but it's going to go real quick. So, wave, basically any disturbance or continuous disturbance of water. A lot of people get nitpicky and go, it's got to be sequential and sustained, whatever. Medium, anything that sound goes, or a wave goes through. Sound, or it goes through air, it goes through material, it goes through any matter. Earthquake is just a wave going through the ground. It's just any medium. Mechanical waves always require a medium. Without a medium, you can't have any wave. It's one of the great arguments of any space movie. There's a loud explosion, and oh look, it's explosion, it's loud, it's great. No, space, there's no medium to travel through, so there's really no sound if it has an explosion. Kind of a bummer, and honestly, it doesn't make a good movie. Electromagnetic waves, however, don't need a medium. We'll talk about the kind of basically properties of light, how it's a photon, how it's a wave. We'll get a little bit bent around the axle when we come back to those. So that being said, those are your definitions you really should know. We do have a few more. It's called pulse wave. Basically, it's a single traveling pulse. I liken it to when you have a slinky, you like basically bounce it towards the other person. It's a pulse wave. Almost everyone, when you sit there and go do anything, it's going to be a periodic wave. Example, the actual wave at a football stadium or soccer stadium. When everyone moves that undulating movement up and down repeatedly, there you go. Now, here's the sine wave. Special way when you have simple harmonic motion, it is called a sine wave. It's a standing wave, it's always continuous, should be fairly easy. Again, simple harmonic motion typically is a sine wave. There you go, there's a pretty picture. The hard part for people to understand is the matter is not moving forward and backwards. Example, even when you're in the ocean, you can bob up and down on a wave and not really move. The water isn't moving a lot. It's only moving up and down. The energy that goes through it is, and that's hard for a lot of people to think. The easiest way is to think of it as the particles of matter are moving a little bit forward, a little bit backwards, a little bit forward, a little bit backwards. Hopefully that helped, I don't know. A transverse wave is basically the wave you think about, crest going up and down, a rope being a slinky, anything like going up and down. So again, crest, high point, trough, low point, wavelength is the difference between two adjacent points. Hopefully this is not new. Hopefully it's not shocking because that's like middle school science. All right, longitudinal waves. These are when you use a slinky. As you push forward and it smashes together, you can see that darkened portion and then fly back towards you. That there is a longitudinal wave. Again, this is a little bit different because you have crests are the compressed region, troughs are the stretched out region. Again, right there, Where x1 is, that would be a crest, and x2 would be a trough, and x3 would be a crest, trough. Again, high density, low density areas. All right. Well, should more. There you go. That's the equation I want to see. You've already seen this once. Speed of light equals frequency times wavelengths. Now we're talking about specific waves. Speed of light for wave speed is always going to be 3.00 times 10 to the 8th meters per second. This wave speed can vary anything you want to be. Again, speed of light, 3.00 times 10 to the 8th meters per second. Wave speed of material, well, that's up to the material. It's up to the energy. So we'll talk a little bit more in detail about that. This is a good slide. The little portion that's highlighted in yellow, the greater the amplitude, the more energy. For a mechanical wave, the energy transferred is proportional to the square of the. So to get it into perspective, I believe we'll work with an equation in class. I'm going to have one given to you. So last set of notes is wave interference. This is very simple to understand. It's basically when two waves occupy the same space, they can do one of two things. They can add or they can cancel out. You guys understand this. It's very cool when it happens. Easiest way, constructive interference. Why do they try and get everybody on the beat? Because if everybody is on the same beat, making the same wave at the exact same time, it's constructive interference. This is how you get really loud sounds. Conversely, you get everyone off beat, it's destructive, and as B and C show, hey, it's actually less than the overall wave. So this is actually the idea behind noise canceling headphones. It's not so much destroying the wave as it is reversing it so you don't hear it. So boundaries are an interesting thing we'll talk about specifically in class. It might help you to draw out this diagram versus free boundary versus a fixed boundary. If you notice, for a free boundary, the pulse will always be on the same size. It arrives on the top and it leaves on the top. A fixed boundary, however, goes on the top, hits the object it's anchored to, and then reflects and goes on the bottom. Just kind of a way to think of that. We'll talk more about that when we come back to light and waves. So just be prepared. If you have any questions, go ahead and write them down. We'll talk about them specifically when we get into class. And here's your couple questions in Edpuzzle.